Good evening. We have some exciting news. Recent results from the science instruments on board the Cassini orbiter show that the rings of Saturn are relatively young, coming into existence just 100,000 years ago. On Earth, humans numbered only 25,000 individuals and had just begun upright walking to form tribes. Saturn itself is much older. Like the rest of the planets, Saturn formed from the solar nebula about 4.6 billion years ago. The artwork you see behind me belongs to David Hardy, one of the world's best space artists. It shows the final moments of a Cassini spacecraft at the end of its 13-year mission. You can see more of David Hardy's work at astroarts.com. David is also one of the contributors to the 2018 Yearbook of Astronomy, published in November. You may reserve a copy, if you wish, from Amazon. In a few days' time, on the 15th of September, the Cassini-Huygens spacecraft will end its mission by diving into the clouds of Saturn. The spacecraft has been orbiting the planet for 13 years and has sent back startling data and thousands of images of Saturn and its moons. In this program, we take a look back at the main discoveries as we celebrate Cassini. Firstly, who were the astronomers Huygens and Cassini? Christian Huygens was born in 1629 and was a leading Dutch mathematician and scientist. Huygens used a long aerial refractive telescope to study Saturn, and in 1655 Huygens proposed that Saturn is surrounded by a thin, flat ring inclined to the ecliptic. Using a 50-power telescope that he designed himself, Huygens also discovered Saturn's biggest moon, Titan. Giovanni Cassini was born in 1625 and he was an Italian astronomer. He was the first appointed Astronomer Royal at the Paris Observatory. Cassini was the first to observe the division in the rings of the planet, which is named in his honour, the Cassini division. And he also discovered 4 moons of Saturn, Iapetus and Rhea, in 1671 and 1672, along with Tethys and Dione in 1684, which he called Sidereal Laodiceae, the stars of Louis. The Cassini spacecraft is a joint venture between NASA, the European Space Agency, and the Italian Space Agency. Including the Cassini orbiter and Huygens probe, it is the second largest unmanned spacecraft ever built. It is 6.8 meters high and 4 meters wide. Cassini entered orbit around Saturn on July 1st, 2004, after a 7-year journey. Saturn lies at a mean distance of 1.4 billion kilometers from the Sun and is the 6th planet in order of distance. The world is 116,500 kilometres in diameter, so it is smaller than Jupiter and about 318 times bigger than the Earth. Saturn is less dense than water, about 30% less, so if you could put Saturn into a big enough ocean, it would float. A day on Saturn is about 10 hours 55 minutes long, so atmospheric features are affected by high velocity winds. Colour imaging shows that the familiar yellow ochre appearance of Saturn gave way at cold winter latitudes to blue hues more reminiscent of Uranus and Neptune. This blue colour is derived from skies clear of aerosols, meaning that sunlight could travel further through the red absorbing methane gas in Saturn's atmosphere, leaving only blue light to be reflected. Like Jupiter, Saturn is a gas giant and lacks a solid surface, although it may have a solid core. Saturn's rapid rotation causes the planet to be flattened at the poles, and the planet bulges at the equator. Saturn has an orbital period of 29.7 years, with the southern summer solstice occurring in October 2002. The atmosphere has plenty of hydrogen and helium gas accreted when Saturn formed 4.5 billion years ago. Mixing it are trace elements of methane, water, ammonia, hydrogen sulfide and phosphine. Some of these condense in the lowest regions of the atmosphere to form cloud decks, starting with water ice at the deepest levels, followed by a stable compound called ammonium hydrogen sulfide, and then ammonia ice in the cloud tops. As a direct consequence of cloud condensation, the ammonia, hydrogen sulfide and water are seen only in small quantities above the clouds, with deeper reservoirs hidden far below the levels that Cassini could reach. The temperature, pressure and density inside Saturn causes hydrogen to change into a metal. Planetary computer models suggest that the interior of Saturn has a small rocky core surrounded by hydrogen and helium. The diameter is thought to be 25,000 kilometers. The core is surrounded by a liquid metallic hydrogen layer, followed by a fluid layer of helium molecular hydrogen that gradually changes to a gas with increasing altitude. The outermost gaseous layer of Saturn is about 1,000 kilometers deep. Saturn has a hot interior reaching 1,200 degrees centigrade at its core, and it radiates more heat into space than it receives from the Sun. Jupiter's thermal energy is generated by slow gravitational compression, although this may not be sufficient to explain heat production for Saturn, as it is smaller than Jupiter by 11,000 kilometers. Saturn's dull atmosphere occasionally displays long-lived ovals and other features. In 1990, the Hubble Space Telescope imaged an enormous white cloud near Saturn's equator, which remained visible for a considerable time. The winds in Saturn's atmosphere are the second fastest among the solar system's planets. Cassini data indicate that peak easterly winds are 1,800 kilometers an hour. Images from Cassini's show that Saturn's northern hemisphere displayed a bright blue hue similar to Uranus and Neptune. Temperature measurements have shown that the south pole of Saturn has a warm polar vortex. While temperatures on Saturn are normally minus 185 degrees centigrade, the temperature of the vortex reaches minus 122 degrees centigrade. Saturn's poles experience the most extreme seasonal changes than anywhere else on the planet, with 15 years in the darkness of the polar winter, followed by 15 years in summer sunshine. Cassini's unique vantage point revealed that tropical compact cyclones exist, locked at both poles of Saturn. Despite the huge seasonal swings in temperature, these storms, identified by their high temperatures in thermal images, appear as circular vortices with steep hurricane-like centres that lie 3 degrees away from the poles. Their centres are depleted in gases and clouds, which suggest that the atmosphere sinks deep into Saturn at the poles. Now, let us turn to the moons of Saturn. We know that the planet has 62 moons. 53 of these have been given names. Titan is the biggest, and Saturn's second largest moon is Rhea. Titan is 26,000 kilometers in diameter and orbits around Saturn once every 16 days, and it can be seen quite well in small telescopes. Soon after Cassini arrived at Saturn, ESA's Huygens lander separated from the spacecraft and entered Titan's cloud tops on the 14th of January 2005, and then successfully landed on the moon's surface. The first images of a landing site show the area covered with large boulders under an orange sky. The Huygens lander photographed pale hills with dark rivers running down to a dark plain. We now believe that the hills are composed of water ice and organic compounds created in Titan's upper atmosphere by the ultraviolet radiation from the sun, which rains onto the moon's surface. The surface of Titan is darker than expected and composed of water and hydrocarbon ice. The soil visible in the images is interpreted to be rain from the hydrocarbon fog above. The Cassini spacecraft made many close approaches to Titan and used radar to map the moon's surface and science instruments to sniff the moon's atmosphere. Titan is primarily composed of water ice and rocky material, and science data from Cassini show there to be liquid hydrocarbon lakes in Titan's polar regions. The young surface is smooth with a few impact craters, although mountains and ice volcanoes also exist there. The atmosphere of Titan is mostly composed of nitrogen, methane and ethane clouds, along with nitrogen-rich organic smog. On the moon's surface, where the average temperature is minus 180 degrees centigrade, the exotic weather creates surface features similar to those here on the Earth, in the form of dunes, rivers, lakes and seas of liquid methane and ethane. In 2016, the Cassini team announced what they believe to be the tallest mountain on Titan, which is about 1.6 kilometers high. Mountains on Titan occur near the equator in so-called ridge belts. One possible mechanism for their formation is tidal forces from Saturn. The Cassini spacecraft has also taken photographs of other moons of Saturn, so let us now look at some of these. Phoebe is about 213 kilometers in size, and there are some impact craters on its surface. Phoebe is associated with a ring around Saturn that extends from 20 million kilometers from the planet. Phoebe orbits around Saturn at an average distance of 21 million kilometers. Iapetus is 1,470 kilometers in diameter and is the third largest moon of Saturn. It is well known for its unusual two-tone surface. Its leading hemisphere is pitch black, while its trailing hemisphere is as white as snow. Cassini images show that the dark material is confined to a large equatorial area on the leading hemisphere, centered on a 20-kilometer high ridge. Iapetus passes through Phoebus's ring as it orbits around Saturn, so the two-tone effect is due to the material from the ring falling onto the moon's surface. The ridge spans nearly the moon's entire equator. Hyperion is another of the smaller moons of Saturn, which is about 270 kilometers in diameter. Hyperion is Titan's nearest neighbor in the Saturn system. Hyperion and Titan are locked in motion with each other, meaning that while Titan makes 4 revolutions around Saturn, Hyperion makes exactly 3. The moon has an extremely irregular shape and a tan-coloured icy surface resembling a sponge. Its interior may also be partially porous as well. Then there are the 2 small shepherding moons, Pan and Atlas, which are each about 30 kilometers in diameter. They orbit inside Saturn's outer ring. In fact, there are several of these small shepherding satellites that orbit within or just beyond Saturn's ring system. These satellites have the effect of sculpting the rings, and both Atlas and Pan are unique in their appearance. We now come to the moon Enceladus, which is the 6th largest satellite of Saturn. It is about 500 kilometers in diameter and is mostly covered in fresh, clean ice. As a result, its surface temperature at midday can only reach minus 198 degrees centigrade. Enceladus has a broad range of surface features, ranging from old, heavily cratered terrain to young, deformed terrain that formed as recently as 100 million years ago. Most importantly, the moon has a subsurface ocean with hydrothermal vents, which may mean that life exists on Enceladus.
In February 2005, we had our first close flyby of Enceladus, and the magnetometer signal saw something unusual.
What a magnetometer does is it measures the magnetic field in the vicinity of the instrument. We had a look at the wiggles, and they looked strange. The magnetic field of Saturn is moving towards it, and it couldn't penetrate down onto the surface, which was pointing to an atmospheric signature of some kind.
Here it looked like it had a tiny atmosphere. In March, we came even closer, looking for that same strange signal.
What it showed was that the signature, the atmospheric signature we were seeing, was focused at the South Pole. It was almost like there was a cometary plume of water vapor coming off from the South Pole.
People were saying, it's gotta be jets, it's gotta be jets, and the imaging team was saying, no, we don't want to say that, until we're sure. And so we went closer. We came within 175 kilometers of Enceladus.
Then we got the data back, and it was spectacular.
And then we found the evidence. Geysers coming out of the South Pole with water vapor and water ice particles. There were active geysers at the South Pole of Enceladus.
Because we were so close, all of the other instruments were able to take really good data. And we put together all of this data. We saw the cracks, the tiger stripes at the South Pole. We saw heat leaking out from these tiger stripes. On subsequent flybys, we found organic material, dust, water vapor coming out of the plume.
The Cassini discoveries in the first 3 flybys were so amazing. We changed our focus and added 20 more flybys of Enceladus, including 7 through the icy jets. The surprising magnetometer reading led us to the liquid water ocean underneath Enceladus's icy crust. After over a decade of research with Cassini, we now know there's a potential for the ocean on Enceladus to support life. And that has altered the way we think about where life might be found in our own solar system and in the worlds beyond.
The instrument acts like a human nose, analyzing the smell, so to speak, or the composition of the gases in the environment. There was a significant amount of molecular hydrogen. The existence of molecular hydrogen, at least within the Earth's ocean system, is like a food source. It's candy for microbes. They eat the hydrogen, they turn it into methane. And with our findings, we were able to not only find out that there was H2 in the system, but to examine the chemistry that's associated with that process of taking hydrogen and turning it into methane. Here on Earth, the hydrothermal systems, known as white smokers, have water-rock interactions that lead to the release of molecular hydrogen in a similar fashion to apparently what's going on at Enceladus. This is just the final step that shows that there's molecular hydrogen being produced by these same hydrothermal processes, and that molecular hydrogen has the chemical energy to support microbial systems in the interior ocean. It's not demonstration of finding life, but it shows the potential for the existence of life in this interior ocean.
All of the planets of the Sun's family have rings around their equator, although they are delicate and difficult to see, while Saturn's rings are the biggest and brightest in the solar system. The rings extend from 6,600 kilometers to 120,700 kilometers out from Saturn's equator and are about 20 meters in thickness. The rings may be the leftover of a shattered moon of Saturn or a captured asteroid that came too close to the planet and was ripped apart by tidal forces. Some of the ice in the E-ring comes from the geysers of Enceladus. Beyond the main rings, at a distance of 20 million kilometers from Saturn, is the sparse Phoebe ring, which is at an angle of 27 degrees to the rings. And, like Saturn's moon Phoebe, the ring particles orbit in a retrograde manner. Cassini is now low on fuel to power the rocket thrusters that maneuver the spacecraft around Saturn and has come to the end of its 13-year mission. On the 15th of September, Cassini's grand finale will be for the spacecraft to dive into the cloud tops of Saturn. As we say farewell to Cassini, the probe will break up and become one with Saturn, where the spacecraft has made significant discoveries. The good news is that NASA and the European Space Agency are already making plans to send a new mission to Saturn.
One of the key discoveries that the Cassini orbiter and the Huygens probe revealed for us was discovering the liquid lakes on Titan. Cassini was able to look at the lakes, get a sense of the coarse composition of the lakes, but nothing about the organic molecules that are dissolved in the lakes. The Titan-Saturn system mission is a 3-in-1 mission with an orbiter for Titan, a balloon that will float through Titan's atmosphere, and a lander that will splash down on one of the northern lakes of Titan. This mission will actually go into a lake, sample the liquid directly, see what the organic molecules are that are present. The Titan-Saturn system mission also will go to Enceladus, the tinier moon, 1,000 times smaller than Titan, which has volcanoes, geysers essentially, that are spewing material from the inside of this moon outward. And it's a chance to see whether there might be molecules that would indicate that life has actually formed within the source region of these geysers. These geysers have water ice, and we strongly suspect that there's liquid water in the region that these geysers are coming from. We know there are organic molecules there because they've been measured by Cassini. The ability to follow this up quickly is essential because with Cassini-Huygens, we have now trained a generation of scientists who are ready to take a new generation of instruments and capabilities back to Titan and Enceladus and really answer the questions that Cassini-Huygens has left for us. And that continuity of knowledge and of enthusiasm is essential and very difficult to maintain in the outer solar system, because trip times are so long. The Titan-Saturn system mission really is Jules Verne realized. It's a kind of planetary exploration that we have never ever done before anywhere else in the solar system and can only be done on Titan. This mission will touch the human heart in terms of the way it's exploring this fascinating world. It will be floating on the surface of a lake. It will be floating through the atmosphere. It will be revealing the entire surface from orbit at the same time. As we think of exploration, of unveiling a new world, it's exploration in the true sense of the word.
That is all we have time for this month. Thank you for watching. I must also say thank you to artist David Hardy for allowing us to use his recent artwork. You can see more of his work at astroarts.com. In October, the space age is 60 years old, and in next month's programme we look back at the manned space missions from the flight of Yuri Gagarin to the International Space Station. If you like these programmes, please share it with your friends and members of your local astronomical society. Until we come back next month, good evening.